Hello, this is Waqas Rahman, and I'm a PhD student of electrical engineering at the Missouri University of Science and Technology. And today I'm going to present our paper titled Deadband Voltage Control and Power Buffering for Extreme Fast Charging Stations. Well, I'm going to start off with some motivation and background. So voltage fluctuation is one of the most common challenges that an extreme fast charging station or a fast charging station can introduce to the distribution network, and it can result in transient and steady state voltage violations at the point of common coupling. As per latest charging protocols, when an electric vehicle connects or disconnects from the charging station, power swings of plus minus 500 kilowatt are expected that that can result in overvoltage and undervoltage, which can damage the regulation devices and protection devices on the distribution network. Therefore, mitigation of the dynamic and static impact of the extreme fast charging stations is extremely important, and it can help the reliable operation of the extreme fast charging stations, and it can facilitate the widespread adoption of electric vehicles and transportation electrification. Now, in our proposed approach, we use the reactive power compensation capability of the fast chargers to mitigate the voltage violations during the steady state. And in this regard, a deadband-based voltage control is proposed to only regulate the voltage when it violates the permissible limits as per IEEE 1547 standards. So during the implementation of the deadband voltage control, the repeated activation deactivation cycling, which is also known as hunting of the PI controllers, is resolved using the sign of reactive power as a trigger signal to turn off the PI controller rather than using the voltage as a trigger signal. Also, during the voltage control, the power electronic converter's apparent power capacity limits affects the active power that can be imported from the distribution network. So therefore, it may require the energy storage system to operate in the load sharing mode and provide the additional power to completely satisfy the charging demand at the station. And lastly, in order to mitigate the dynamic impact of the extreme fast charging on power quality of the distribution network, a ramp rate based power buffering of the energy storage system is proposed, in which the energy storage system buffers the power swings for the events when the electric vehicle connects or disconnects from the charging station, or during the charging process when the ramp rate of the electric vehicle charging demand violates the permissible limits. So this slide presents the overall control schematic of the charging station, in which the solid connections represent the power lines and the dashed connections represent the control signals and the transfer of measured information between different components of the charging station. So the voltage is computed at the point is measured at the point of common coupling and is compared against the reference, which is being generated from this deadband voltage control block in which, using the equation shown on the top left. So when the measured voltage violates the lower limit of the band, then the reference is set to the lower limit of the deadband, and it is set to the upper limit of the deadband when the voltage violates the upper limit of the deadband. And for the time period when the voltage is within the band, so the voltage control will be disabled. So after comparing the measured voltage with the reference, API controller generates the reactive power and it is sent to the reference computation block. Other inputs of this computation block are the charging load at the charging station, the state of charge of the energy storage system. So this reference computation block generates the active power reference for the dual active bridges and the reactive power reference for the active front end, and the charging and discharging reference for the energy storage system. So using equations shown on the bottom right of this slide, the current references are computed, which are used to realize the flow or exchange of power, active and reactive power between charging station and the distribution network. So inside this rapid control and the reference computation block, the flowcharts which are used for the implemented control are shown on the left on the next slide. So both of these control algorithms work in cooperation with each other, and on the left hand side we can see the flowchart for the rapid control algorithm to operate the energy storage system in power buffering mode. So the charging demand is measured and its ramp rate is computed, and it is compared against the maximum allowable ramp rate limits as per grid code. And depending upon whether the ramp rate is violating either the ramping up limits or the ramping down limits, the energy storage system will be operated in the power buffering mode, and it will absorb the power swings, and it will make sure that the power import from the grid does not violate the allowable ramp rate limits. And on the right hand side, we are seeing the reference computation, a rule-based reference computation algorithm. So depending upon the charging demand and the reactive power uh, uh, from the controller and the state of charge of the energy storage system, corresponding branch of this flowchart is selected, and the active power reference, the reference for the energy storage system, and the reactive power reference for the active front end are computed and sent to the correspond or the related power devices. And moreover, this algorithm also ensures that the state of charge of the energy storage system stays within the range of 40% and 60%, mainly to enhance the battery life and decrease the degradation. So in order to prove efficacy of the proposed approach, 3 case studies were simulated. So the first case study is our base case where none of the voltage control or the ramp rate control are applied. And in case 2B, the deadband voltage control was applied, but for case 2A, the ramp rate control was disabled, and in case 2B, it was enabled. So this slide presents the results of the case study simulations, and in the chart A, the electric vehicle charging load is shown for 3 electric vehicles, and each electric vehicle receives the charging power for about 3 seconds. And for the demonstration purposes, the charging power of 40 kilowatt is selected for each electric vehicle. And chart B and C present the measured active power and reactive power at the point of common coupling. And the case 1 is represented by the green curve, and the case 2A is represented by the red curve, and case 2B, in which both the deadband voltage control and the ramp rate control are enabled, are shown by the blue curve. So from chart D, we can see that the grid voltage at the point of common coupling is violating the permissible limits of the band, which is set as 0.975 for this work. And we can see that when the second electric vehicle connects to the charging station, the voltage violates the lower limit of the band. But for case 2A, we can see that it successfully mitigates the steady state impact of the charging station of the electric vehicle load, and it regulates the voltage to the lower limit of the band. However, we can still see some voltage, a transient voltage drop and transient voltage rise, because the ramp rate in this case is not enabled yet. So for case 2B, we can see that it not only resolves the voltage issues during the steady state, but it also resolves the issues during the dynamic or the transient state. And we can see that the transient voltage drops and rises are disappeared for the case 2B. So this demonstrates the efficacy of the proposed control approach. And from chart E, we can see that the energy storage system is buffering the power for the instances when the electric vehicles are connected to the station or when they are disconnecting from the station. So during the first half of this chart, it is providing power, and during the second half, it is absorbing power. And during this center part of this chart, we can see that it is acting as a load sharing device to provide the supplemental power, because the apparent power capacity of the power electronic converters is maxed out. And chart F presents the DC link voltage, where we can see that the case 2B has successfully mitigated the transient impact of the electric vehicle charging demand. So to conclude my presentation, this paper presents a joint solution to mitigate the steady state and transient impact of the extreme fast charging station, and a deadband voltage control makes sure that the electric power compensation is only enabled when the voltage violates the limit of the band. And lastly, the energy buffering application of the energy storage system makes sure that the voltage sags and swells are mitigated. Thank you. If you have any question, please let me know.